galvanometer is a device by which we can detect a current through a circuit, right, through a branch. We can detect whether there is a current or not, whether the current is very large or very small current. Whatever, we can detect current through a circuit or through a branch of a circuit by a galvanometer. Actually, there are two types of galvanometer. One is called moving coil galvanometer and another is called moving magnet galvanometer. As is the name, the moving coil galvanometer, here coil will be moving by the amount of rotation of the coil. We can measure the current, right? Now where it will rotate? It will rotate in a magnetic field. If we place a, we all already discussed, if we place a current carrying loop or current carrying coil in a magnetic field, then it will rotate, right? And applying that principle, if we develop a device or develop a galvanometer, that is called the moving coil galvanometer. And another type of galvanometer, which is called moving magnet galvanometer. Here, as is the name, here magnet will be moving, and magnet will be moving in a magnetic field produced by a current carrying loop. We already know that if a current flowing through a wire, then it produces a magnetic field, and in that magnetic field, if we place a magnetic needle, then it will rotate. By the amount of rotation, we can measure the current, and that is the moving magnet galvanometer. But now today we are going to discuss the moving coil galvanometer. Moving coil galvanometer. MCG, moving coil galvanometer. Moving coil galvanometer is a device. We have already told that moving coil galvanometer is a device used to detect or measure small electric current flowing in the electric circuit. It is based on the fact or the principle that when a current carrying coil or loop is placed in the uniform magnetic field, it will experience a torque. Clear? Now, a coil on a non-metallic frame is suspended between the two poles of a permanent magnet, and the poles are or the poles of the magnet will be cylindrical, so that the region between the pole has a uniform magnetic field. Actually, poles are like this. This is one pole and this is another pole. This is north pole and this is south pole. And this is the region between the two poles in which there is a uniform magnetic field. Right? These are the, it may be a U-shaped horseshoe shaped the magnet, so that the magnetic field will be very large, or intensity of the magnetic field is very large. And here magnetic field will be radial, like this will be the field lines. Right? So that here the magnetic field will be uniform. And now if we place a current carrying coil here, then it will experience a torque and it will try to rotate. Right? Permanent magnet, and the coil is suspended by a hair-like spiral spring. Generally generally made up of phosphor bronze oil, phosphor bronze, because this phosphor bronze has the very small restoring torque, and by very small restoring torque we can increase the sensitivity. In later discussion we will discuss. Now what I have told, that the coil is suspended by a hair-like spiral spring generally made up of phosphor bronze, which acts as path of the current of the coil. Right? Now see here, leave that. Now this should be cylindrical, or you can this. Now here we place a what? Coil, and this coil may have number of turns, may, and one end of the coil is connected, or this is suspended. This is a spring, right? One end of the coil is connected to the spring, and the spring is connected to a terminal of the galvanometer. This is the case, and another end of the spring is connected to another terminal. Now these two terminals will be connected in the outer circuit or external circuit. Here is a magnetic pole, north pole, south pole, or this is north pole, this is south pole. We just place here a coil, and this coil is suspended by a hair-like spring, which is generally made up of phosphor bronze, and the spring, this is the spring, and one end of the spring is connected to one terminal of the galvanometer, and another terminal of the spring is connected to another point, that is another connecting point of the galvanometer. Now we just add the external circuit between this T1 and T2. Then when we connect on the T1, it is connected to the hair-like spring, right? And that is connected to the coil, and another is to the coil. Then current will be flowing through the coil. If there is a current through the external circuit, then that will pass through this coil. Clear? This is the main structure. Actual structure will be different, it will be modified, but outline of the structure is this. Now if this is spring, then it is called the table galvanometer, table moving coil galvanometer. It is just you have shown in your lab, just small device. There is only, you see only 2 points, and you see another thing is there, that this spring is connected to a pointer, right? This spring is connected to a pointer, and that pointer will rotate if the spring is rotating. If the spiral spring is rotating, then that pointer will rotate, right? Now see here, a piece of soft iron is placed within the frame of the coil. Within the frame of the coil, we place a soft iron so that its magnetic field can increase. If we place a soft iron, then magnetic field produced by the coil will increase. A plain circular mirror is attached below the pointer. Here is a pointer, and here is a scale, and below the pointer there is a mirror. This is the mirror, and this is the scale. Right? A plain circular mirror is attached below the pointer to note the deflection of the coil using the scale arrangement. This is one type of. And another type of moving galvanometer, which is called suspended coil galvanometer. In that case, the coil is suspended from a point of suspension from the ceiling by the phosphor bronze here like spring, right? Here like thread, and that thread is connected. One end of the thread is connected to the external circuit, and here the other end of the coil is also connected to the external circuit. Is it clear to you? This is the magnet, and in this region there is a magnetic field, and here is our coil, rectangular or circular coil. One end of the coil is connected to the thread of the phosphor bronze thread, and other end going to the external circuit. And now this arrangement is suspended from a ceiling and hanging here near a wall, and in front of that arrangement we have a table and a scale stand. In that stand there is a light setup and also a scale setup like this. See here, this total system is suspended from the ceiling and attached to the wall or near the wall. Here we place a table, and on the table we put a stand. In that stand, like this is a stand, and in that stand we put a light system, right? Light will focus on or going to the this thread, and there is a scale system also. Here is a scale. Clear? Now, in the phosphor bronze thread in which the coil is suspended, there is a small mirror. If light falls on the mirror, then it will reflect, and that reflected light will fall on this scale, and from here we can see the spot of the light. When there is no current, it will be so adjusted that light will be on the 0 point, at this point 0. Now if there is a current, then this coil tries to rotate. Clear? Tries to rotate, and if the coil is rotated, when the current flows through the coil, it experiences a torque, and by that torque the coil tries to deflect or tries to rotate, and the torque tries to deflect the coil is called the deflecting torque. As the coil gets deflected by the elasticity of the spring, it tries to restore its position. As the coil gets deflected, the spring is twisted, and by the virtue of elasticity, it tries to come back its original position. That means a restoring torque is developed in the thread. If A is the restoring torque per unit twist, then the restoring torque will be K into phi, and the torque acting on the coil due to the magnetic field, we know that. We are coming to that calculation also. Now in equilibrium, this restoring torque and deflecting torque will be same, right? So the for the suspended coil galvanometer, the thread will be twisted mirror will be rotated. Mirror will rotate. Now if mirror will rotate, this is the incident ray. The direction of the incident ray is same. Mirror is rotated, then reflected ray will be rotated, right? If angle is rotated by theta, then reflected ray will be rotated by 2 theta. So the reflected light will be shifted, and from the scale we can measure the shift of the light, and by that we can measure the current. That is the suspended coil galvanometer. Now we are discussing the stable galvanometer, which we uses in our laboratory, right? Now let us see. V is the intensity of magnetic field. This is the intensity of magnetic field, right? I is the current flowing through the coil. I is current flowing through the coil. L is length of the coil. V is the breadth of the coil. So A, capital A is equal to L into B is the area of the coil. We have taken the rectangular loop. That's why the area is L into B. And N, capital N, is the number of turns in the coil. Right? Now we have taken here a spring. When current flows through the coil, it experiences a torque, and that torque is given by tau is equal to what? N Bia sin theta. Right? We have proved that. Have we proved this? If a rectangular coil of area A is placed in a magnetic field of strength B, and number of turns in the coil is N, I is the current, then the torque experienced by the coil is tau is equal to N Bia sin theta, where theta is the angle. Theta is the angle made by the normal to the plane of the coil with the direction of the magnetic field. If this angle is 90 degree, which is the initial position, that is, if this is the direction of from left to right, this is the direction of the magnetic field, then the coil is in this position. No, coil is in this position, right? This is the coil. Then direction of the coil is this, which is the perpendicular to the plane. This is the direction of or normal to the plane of the coil, and this is the direction of magnetic field. The angle between the two is 90 degree. So in that case, tau will be equal to NBIA if theta is equal to 90 degree. This is the initial position, right? Then tau is equal to NBIA. Now this amount of torque tries to deflate the coil and is known as deflecting torque. This is the deflecting torque. As the coil gets deflected, the spring is twisted. Spring is twisted, and a restoring torque is developed in the spring due to its elasticity. If K is the restoring torque per unit twist, then restoring torque for the deflection of phi, if phi angle is deflected, then restoring torque, that is tau dash, is equal to K phi, where phi is the angle of deflection. This is restoring torque, right? This comes why? This comes due to the elasticity of the spring. Now for equilibrium of the coil, this deflecting coil will be equal to the restoring torque. Deflecting torque will be equal to the restoring torque. And NBIA will be equal to K into phi, and from here you can say I is equal to K phi by NBA. Now from here you can write I is equal to G phi, where G is equal to K by NBA is called the galvanometer constant, because these all are associated to the galvanometer. For a particular galvanometer, these terms are constant. K is the restoring torque per unit twist, N is the number of turns, B is the intensity of magnetic field, and A is the area of the coil. All are constant, right? Thus deflection phi of the coil is directly proportional to the current flowing through the coil. Hence, we can use a linear scale in the galvanometer to detect the current in the circuit. Clear? See here. If there is phi, then you can say there is a current. And measuring the phi, measuring the angle of deflection, you can measure the current. In the suspended coil galvanometer, just measure the shift of the reflected light. If the shift is d, small d, then angle of rotation of the reflected ray is d by capital D, where capital D is the distance of the scale from the mirror. Right? You can measure that. And therefore, you can say if the twist in the thread is phi, then rotation of the mirror is phi. So, the rotation of the reflected ray is 2 phi. So, 2 phi is equal to d by capital D, and phi can be equal to d by 2d. Just put this here and you get the current. This is for the suspended coil galvanometer. Sensitivity of galvanometer. Now, a galvanometer is said to be sensitive if a small current flowing through the coil, of the galvanometer produces a large deflection. Then it is called highly sensitive. Right? Now, this galvanometer has two types of sensitivity. One is called current sensitivity and another is called voltage sensitivity. First, we are going to define the current sensitivity. The current sensitivity of a galvanometer is defined as the deflection produced in the galvanometer per unit current flowing through it. Now, see here, we have discussed here that I is equal to K phi by NBA. Now, current sensitivity. Current sensitivity is the deflection produced in the galvanometer per unit current flowing through it. That means phi by R. This is called current sensitivity. Let us say IS. Let us say this IS, current sensitivity. IS is equal to phi by R. Deflection produced by the unit current through the galvanometer or through the coil of the galvanometer. And that can be written as phi divided by I is K phi by NBA, and that is NBA by K. Right? Phi cancels out and NBA by K is called the current sensitivity of the moving coil galvanometer. And see here, the current sensitivity of the galvanometer can be increased by increasing the magnetic field, by using the strong permanent magnet of horseshoe shape. If the magnet is horseshoe shape, then its magnetic field is larger than any other permanent magnet. By increasing the number of turns of the coil, by increasing the area of the coil, and by decreasing the restoring force or restoring twist, restoring torque per unit twist by decreasing the restoring force constant. Restoring force constant is K. Is it clear? That's why we are using the phosphor bronze thread, which has the low restoring force as well as it is conducting. This is the current sensitivity. Now, what is voltage sensitivity? Now, the voltage sensitivity, let us say, this symbol is Vs, put a symbol Vs. Now, what is voltage sensitivity? Voltage sensitivity of galvanometer is defined as the deflection produced in the galvanometer per unit voltage applied to it. If we apply unit voltage, that is 1 volt, to the galvanometer, then what is the deflection of the galvanometer? Then deflection of the galvanometer divided by the unit voltage, that means 1, is called the voltage sensitivity. Voltage sensitivity of galvanometer is defined as the deflection produced in the galvanometer per unit voltage applied to it. That means Vs is equal to this. This is the deflection, this is the voltage applied. And that means deflection per unit voltage. That is phi by V. And we know that V is equal to I. R is the resistance of the galvanometer. Therefore, phi by R into I is equal to K phi by NBA. And this is NBA by KR. You can also write this as phi by I is equal to IS. You can also write this as IS by R. That is current sensitivity by the resistance of the galvanometer. Now, again, if we want to increase the voltage sensitivity of the galvanometer, then I have to increase the number of turns of the coil, the intensity of magnetic field produced by the permanent magnet, and the area of the coil. And by decreasing the K, that is the restoring force of the thread, and the R, that is the resistance of the galvanometer. By decreasing K and R, we can increase the voltage sensitivity. By increasing N, B, A, we can increase the voltage sensitivity. Right? These are the two types of sensitivity of the galvanometer.